Okay, we're going to tackle this question here that has to do with voltage drop. So we've talked at length on how to on what voltage drop is. It's the voltage that is lost in the conductors due to the internal resistance of that conductors. So for example, if you have a 120 volt source going to a light bulb, but it's far enough away and the length of this conductor is pretty substantial, then you're going to have this conductor is going to be made up of resistance. And that resistance multiplied by the current going through, let's say there's 10 amps and there's 0.1 ohms going through of resistance in this particular conductor to the lamp, then that means there's going to be a 1 volt drop on that conductor, and on the conductor coming back to the source. So if we got 1 volt drop there and another volt drop coming back, we actually only have 118 volts at the source, because our voltage drop on our conductor plus our voltage drop on the load, the voltage drop on that conductor need to equate to our voltage source. So there's a rule in the code that talks about not exceeding a 3% voltage drop on a particular branch circuit. So we can never have, in this particular case, if we took our 120 and multiplied it by 0.03, we would not be able to afford more than a 3.6 volt drop on our conductors. Otherwise, we would exceed that 3% drop that we're allowed. So 120 minus 3.6 would be 116.4. So we would have to have at least 116.4 volts on this light for it to be up to code. Now, we haven't talked much about calculating the distance that you can run a conductor and not exceed that 3% voltage drop. But I want to touch on that now so that you might know it for if it comes up on the test for whatever reason. Hopefully it doesn't, but it may. So in this particular question, we got TW75 copper conductors, and they're required to supply 25 amps, 120 volt continuous load, 30.4 meters from a distribution panel. So that's referring to a particular, if you got a panel here and potential light bulb over here, we can't be more than, our light bulb is going to be 30.4 meters from our panel. Okay, our current going to that light or load is going to be 25 amps. And the voltage drop cannot exceed 3%. And this is important here. Equipment is not marked for maximum temperature ratings. So we got to take, when we're dealing with our ampacity, we got to take from the 60 degrees Celsius column, because we don't know what the termination ratings are. Okay, so let's go over to the code, and rule 8-102 deals with voltage drop. So this rule here is saying that we're only allowed no more than 3% voltage drop in a feeder or branch circuit. All right, so the way that we calculate that is we got to go to Appendix D. So Appendix D, and we're going to use Appendix D3. D3 is a particular table that deals with the distance to the center of distribution for a 1% drop in voltage on a nominal 120 volt 2 conductor copper circuit. So for instance, we are dealing with 25 amps here, and if we don't want to exceed a 1% drop, then we could use number 12 conductor, but only to 3.9 meters. That's not very far. And that's going to get us to a 1% voltage drop on that conductor. Now, we're allowed 3, so we would multiply this number here, 3.1 by 3, because we're allowed a 3% drop, which would give us approximately 9.3 meters. Now, as we know, we want to, if we go back to our question, we got to run at 30.4 meters. So number 12 conductor is not gonna cut it. What about number 10? So again, 6.2 meters, we can run number 10 with 25 amps on it and not exceed that 1%, or with the 1% voltage drop. So we're dealing with 3%, so multiply the 6.2 by 3. That's going to give us 18.6 meters. And again, we're not too close to what we need. Okay. What about the number 8? If we go to the next column, we're allowed 25 amps. We're allowed to run that number 8, 9.9 meters, and not exceed a 1% voltage drop. So again, we're dealing with 3, so 9.9 times 3 gives us 29.7. But what we got to do here, obviously that 29.7 isn't going to give us the 30.4 meters that we need. But if we scroll down on this particular rule, it's important we read this here. Because the distances in table D3 are based on conductor resistance of 60 degrees Celsius, these distances must be multiplied by the correction factors below according to temperature rating of the conductor insulation used and the percentage load with respect to the allowable ampacity. Okay, so we are dealing with 25 amps. But what we need to figure out is the percentage of what a number 8 copper conductor running a raceway can handle. So we're going to go to table 2. Let's see if there's... Okay. And figure out what the allowable ampacity of a copper conductor, number 8 copper conductor is. So we're dealing with number 8, or we want to see if number 8 will work for 30.4 meters. We know that the allowable ampacity of that is 40 amps at 60 degrees Celsius. And we got to use the 60 degrees because our termination points are unmarked. So we got to go with the lowest temperature rating. So that number 8 is good for 40 amps. So we're going to take, if we go back to our formula here, or subrule note 3 on that particular table, we're going to take our 25 amps that we need in that circuit and divide it by 40 amps, which is what number 8 is capable of carrying, and that's going to give us a percentage. So 24 divided by 40, 25 divided by 40, it's going to give us 0.625 or 62.5%. So we've only loaded up that number 8 to 62.5% of what it's capable of. So where the calculation allowable ampacity fall between two columns. So we're going to go to we're at 62.5%. If it falls between two columns, a factor in the higher percentage column shall be used. So we're going to go to the higher column, number 70. And our temperature rating of the conductor is 75 degrees. So this time we don't have to account for the termination points. So we're going to use this multiplier in our calculation. Okay. Down here on note 9, it gives us an example of using this calculation. So in our particular case, we're going to see if number 8 will work. If we go back up to the table, number 8 at 25 amps is good for 9.9 meters. Now what we're going to do is we're going to multiply by 3, that 9.9, as we were doing before, because that table deals with a 1% drop, and we are able to use a 3% drop. We're going to multiply it by this multiplier, 1.03, because our number 8 is capable of carrying 40 amps, but we're only putting 25 amps. We can multiply it by that 1.03. And because this table utilizes 120 volts, so a drop in voltage on nominal 120 volts, and our particular circuit uses 120 volts, then we're going to be 120 over 120, which is 1. So written out, it's going to look like this here. So number 8 at 25 amps is good for 9.9 meters at a 1% drop, multiplied by 3, because we're allowed 3% drop, multiplied by our multiplier, because the 25, we only got 25 amps in a number 8 that's rated for 40 amps, and multiplied by 120 over 120, which is 1, which gives us, this is going to give us the length that we can run that particular load from the distribution panel. So 9.9 times 3 times 0.03 times 1 equals 30.591 meters. So if we go up to the question, what's minimum size TW75 copper conductors are required to supply 25 amps, 120 volt continuous load, 30.4 meters. So we've exceeded that 30.4 meters using number 8 if the voltage drop is not to exceed 3%. So we are able to use number 8 TW75 copper conductors for that particular load. If we use number 10, we would exceed that voltage drop on that particular load. So number 8 is the bare minimum that we can use in this particular circumstance to get us 30.591 meters away from the distribution. Okay, hopefully that helps. It's a little convoluted. It takes a little bit of trial and error. As you can see, I had to calculate for number 8. If that wouldn't have worked, if it would have been less than 30.4, then I would have known that I have to go up to the next size conductor and see if that worked. But fortunately, number 8 works for us.